Guys, in this video, we are going to talk about IMFs. We're going to talk about the three kinds of IMFs, and then also talk about how to identify what types of IMFs are in different compounds. You might want a periodic table for this, but let's get started. Okay, guys, so IMF stands for intermolecular forces. So what we're going to talk about really quickly in this part of the video is intramolecular versus intermolecular. Okay, guys, so intra is like inside, all right? So intramolecular forces are attractive forces within a molecule. So basically, like how I think of them is that this is what holds the molecule together. Holds molecule together. Oh my goodness, spelling is hard. All right, so that's what holds your molecule together. And we have three different types of intramolecular forces. We have ionic bonding. That occurs between a metal and a nonmetal, and it's where electrons are actually transferred. And then we have covalent that occurs between two or more nonmetals, and that's where electrons are shared. And then finally, we have metallic, and in metallic bonds, that's where we get that nice sea of electrons. So this is what actually keeps our molecules together. So that's what keeps like your salt, your Na and your Cl. It's what keeps those two compounds held together. So it's inside a molecule itself. Intermolecular forces are the forces that attract the molecules to other molecules. So like if I'm talking about water, it's what attracts one water molecule to another water molecule. It's the intermolecular forces. Now guys, we're going to talk about the intermolecular forces, but I want to address a common misconception right now, and that is about phase changes. So phase changes, like going from a solid to a liquid or a liquid to a gas, are changes in intermolecular bonding, physical changes, not in intramolecular bonding, chemical changes. So one of the most common misconceptions that we see is talking about like water. So if I have a liquid water, looks like this, all right? It's my little liquid water molecules, right? And I'm going to have, they're going to be like relatively closely packed together in a liquid. We're actually going to talk about solids, liquids, and gases a little bit later this unit. But whenever they, just drawing my little Mickey Mouses, whenever they turn into a gas, they start to heat up. And what a lot of people think happens is that we form, hydrogen gas and oxygen gas when it starts to boil, and that it separates out into those different gas types. But that is not what happens. What instead happens is that our water molecules, that heat begins to overcome those intermolecular forces, and instead of breaking apart into hydrogen or oxygen, what happens is that our water molecules, they're breaking those forces of attraction, so our water molecules just start to separate and break down those intermolecular forces, and so they just spread apart and become gas particles. Okay, so now let's jump in to those different types of intermolecular forces. So intermolecular forces are those attractions between particles, and it's different things, atoms, molecules, or ions, because if it's an atom, it's like an element, molecule, covalent compound, and then ions are ionic compounds. So these are the things that hold those together. So they hold one molecule to all the other molecules surrounding it. They vary in strength, but they're generally weaker than intramolecular bonds or forces. Like 99% of the time, they are weaker than the bonds that actually hold molecules together, but occasionally they are stronger. So, yeah. And there's three types here. We have London dispersion forces, dipole-dipole, and hydrogen bonding. London dispersion forces are a temporary attraction, and we're going to go in more depth on all of these, but I'm just kind of giving you a very brief rundown of them, are temporary attraction, and they happen on non-polar compounds. Okay, between non-polar compounds. And then dipole-dipole is attraction between polar compounds. And finally, last but not least, hydrogen bonding. Hydrogen bonding is a special form of dipole-dipole. And hydrogen bonding occurs between hydrogen when it is bonded to fluorine, oxygen, or nitrogen. It's the only time we have hydrogen bonding. And obviously, since it's a special type of dipole-dipole, they also have to be polar compounds. All right. So the intermolecular forces are once again between molecules. They are not a bond. All right. In intermolecular forces, they're not as strong. They are when you break intermolecular forces, it is a physical change, because typically when we're breaking intermolecular forces, what we're doing is we are changing phase, but it is a physical change. And what you guys will notice is down here, I have hydrochloric acid changing phase from hydrochloric acid changing phase from a liquid to a gas. All right. And what happens when we go from a liquid to a gas is if I have like hydrochloric acid, all right, looks kind of like that. All right. In its liquid phase, they're all going to be, the particles are going to be pretty close together like this. And then again, when it breaks apart into a gas, those particles aren't breaking apart, but they are just like spreading out. So they're spreading out and becoming a gas. Versus on the second reaction, where I'm actually breaking apart into hydrogen and chlorine. So we start the same way with our hydrogen and our chlorine bonded together. And then when they undergo that reaction, they actually break apart into separate elements. And you'll see it takes a lot more energy to break them apart into their separate elements than it does just to change their phase and to break those intermolecular forces. So there's much more energy in bonds than there is in those intermolecular forces, the IMFs. All right, so let's get into talking into more specifics about each type of IMF here. So our first one we're going to talk about is dipole-dipole forces. So dipole-dipole forces are found between molecules that are polar. And in our polar molecules, we have what we call a dipole, and it's the regions of slightly positive and slightly negative charge. So it's where we have that unbalance of electrons. Because remember, it's kind of a tug of war match in between your electrons, and the ones that are more electronegative are going to have those electrons more often than those that are less electronegative, leaving us with that slightly negative, because that electron is more often on that side, and that slightly positive side. If you're a little confused on polarity, definitely go check back Unit 2 videos. There should be a video on polarity. Check that and to make sure you understand, because it is going to be really important. But because we have that slightly negative and that slightly positive, they feel there's attraction from one molecule to another. So to kind of draw it out, I'm going to say I have a slightly negative side to all of my molecules. And then I have a slightly positive side on my molecules. And my negative side is going to be attracted to that slightly positive side. So since those are attracted, we kind of get that interaction there, because the slightly negative side is attracted to the slightly positive side of another molecule. And so we have that attraction there. And then it just says, just a definition of like, well, what is a dipole? If we have dipole-dipole forces, guys, a dipole force is an attraction between polar molecules. So we have that slightly positive and that slightly negative that leads to an attraction, because positives and negatives attract. Okay? And then we have hydrogen bonding. Hydrogen bonding are dipole-dipole, but they are a special type of dipole-dipole that is stronger. And they only contain between molecules that have hydrogen bonded to nitrogen, oxygen, and fluorine in a compound. Now, guys, I do want to make a note here that especially if you're looking at a really long like bond, if you're looking at like a really, it's not, let me try that again, a really long like carbon chain here that a lot of times it may look like it has hydrogen bonding because it has oxygen and hydrogen on the end of it, but you need to make sure that it is an accessible. So you need to make sure that the bond is accessible, especially in really long chains. So if it's not accessible, it's not going to have hydrogen bonding because we're not going to be able to get to that slightly negative region. Really, it's typically with the oxygen. You can't get to the oxygen. If it can't get that slightly negative charge, it can't be attracted to the slightly positive of something else. So that's really only for really long chains of carbon. Okay. And then our last one is London dispersion. So London dispersion forces are the attraction that results from the constant motion of electrons. And basically, the electrons create what we call instantaneous dipoles and induced dipoles. London dispersion forces happen between all atoms and molecules. Polar, non-polar, whatever. They happen between all of them. And for this one, guys, I want to show you guys a little video about what happens in London dispersion forces. So I'm gonna see if it will work. Okay, so this is a little video that is just an animation that shows us London dispersion forces and what's going on. I've tried to make it bigger, but it won't go any bigger. So sorry, guys. So you guys can see your electrons are in constant motion. Every once in a while, our electrons will line up kind of on the same side. And when they do that, they create what we call a dipole. And it's just because we have a higher region of negative charge. So what will happen is as our electrons are moving, they'll create those dipoles that have those slightly negative and those slightly positive. And when that happens, they create kind of a charge from the positive and the negative sign up, and it creates a weak attractive force. Now, electrons are constantly moving, so this is going to happen several times, even if it seems like it shouldn't. So that's dipole and how they're formed. Okay, so now we're going to try to draw those London dispersion forces. So basically what happens is all of our electrons kind of congregate to one side, and I'm just drawing my electrons as negative signs. All of our electrons kind of congregate to one side, and that leaves us with a slightly negative charge on that side and a slightly positive charge on our other side, which then leads to that momentary attraction. Now, guys, there's a few notes that we need to make about London dispersion forces here. So, London dispersion forces are the only intermolecular force between nonpolar molecules and noble gases. All right, so London dispersion forces happen between all molecules, but it's important to know that they definitely are the only ones that happen between nonpolar and noble gases. Okay, and then, guys, how strong our dipole is depends on a couple of factors. So how strong that negative and that positive charge are going to be depends on several factors. So the first one is the polarizability of the electrons. So what that means is how likely is my electron cloud to create that dipole, or to have that dipole happen, that electric field to take place, basically. And that depends on two factors. How many electrons we have. So the volume of the electron clouds. How big is our electron cloud? And how big is our electron cloud? And then the second one is how many electrons are in our electron cloud. So the more electrons that are in your electron cloud, obviously the more likely you are to have that dipole moment. The more likely you are to have electrons. The more that are moving, the more likely you are to have that moment. And then the more electrons that are on one side, obviously the stronger the dipole. So what we look at is the largest molar mass. So the larger the molar mass, that means there's more electrons, which means that we're going to have increased polarizability, which is going to lead to stronger attractions. And then the other thing is the shape of the molecule. The more surface contact you have, the larger your dipole is going to be. So those really long carbon chains that are in organic molecules are going to be much more likely to have a stronger dipole than like molecules that form rings or things like that. So the more surface area you have, the better it's going to be. The more likely you are to be able to have that increased polarizability. So yeah. So guys, now what's important for us to talk about is how to tell. We learned about our intermolecular forces, so how are they in play? How do we determine them? So the first thing that you need to know is you need to be able to determine the polarity of the molecule. So guys, once again, if you don't understand polarity, go check out our video on Unit 2 over polarity. After you've determined the polarity, we can determine the intermolecular forces. So if it's nonpolar, then the IMF is London dispersion automatically. If it's polar, then the IMF is dipole-dipole. And if it's polar and the bond is hydrogen, oxygen, nitrogen, and it's attached to hydrogen, then you have hydrogen bonding. Okay? Now guys, really quickly before we kind of wrap this up and do a little practice, I want to talk about a few more things. So the first one is metallic bonding. Metallic elements are going to have those metal cations and a sea of those mobile valence electrons. Ionic bonds are cations and anions, which is usually a metal and a nonmetal, held together by their Coulombic attraction. And then last are covalent network bonds. Those are extensive covalent bonds that occur. Basically, they result in like really giant molecules. That's just extensive covalent bonds that occur, and it's really strong type of bonding. We are going to talk about all of these later in our unit. So like in the next few days, we're going to talk about those 3 types of bonding, but we do need to talk about the strength of attraction. So our weakest attraction to our strongest attraction in general, London dispersion forces are going to be your weakest, then dipole-dipole, then hydrogen bonding. After that, then we have our actual types of bonding. So metallic bonding, ionic bonding, and covalent network are going to be much stronger. So we go from weakest is our London dispersion to strongest with our covalent network. Now, if I have 2 molecules and I ask you which one has like a stronger has stronger forces of attraction between the molecules, and it's the same IMF, we have to look at the molecular weight. The heavier the particle, the stronger the IMF. But we only think about that and compare them that way if we are comparing the same type of IMF. So what I want you guys to do right now is we just talked about the 3 types of IMFs, London dispersion, dipole-dipole, and hydrogen bonding. So I want you guys to go ahead and fill out this chart right here with your summary of what you've learned so far. So go ahead and fill out this chart. Okay, guys, so London dispersion forces happen in all compounds, polar and nonpolar. Dipole-dipole are only between polar compounds, and hydrogen bonding is polar compounds with hydrogen bonded to nitrogen, oxygen, and fluorine. Hydrogen bond are our strongest IMF, with London dispersion being our weakest. So now we're going to do a little bit of practice where we determine the intermolecular force in the following substances. So we're going to start with hydrogen. So I need to start by drawing my, determining the polarity. Right here I have H2, so it's hydrogen bonded to hydrogen. It's going to have, that's what my Lewis structure looks like. Obviously, guys, these are going to have the same electronegativity since it's the same element. So hydrogen H2 is going to be a nonpolar compound. Since it is nonpolar, the only type of intermolecular forces that are in between here are going to be those London dispersion forces because it's nonpolar. So that's all it can have. Next, we would have HCl. So HCl, all right, we have hydrogen bonded to, all right, guys, chlorine has a much higher electronegativity than hydrogen does. So that means our chlorine is going to have that slightly negative charge, while our hydrogen has that slightly positive charge. And so this one is going to be a polar compound. And it does have hydrogen, but it's not bonded to nitrogen, oxygen, or fluorine. So this one would only have dipole forces between it because we don't have that nitrogen, oxygen, or fluorine. Next we have Fe. Fe is a metal, so it's going to experience metallic bonding. Okay. Next we have H2S. And I'm just going to quickly draw my Lewis structure here. And it looks like this. And so H2S is a polar compound. So our S has that slightly negative charge, and our H has that slightly positive charge. So we do have a polar compound again. So since it is polar, it does have hydrogen, but again, doesn't have that nitrogen, oxygen, and fluorine. So the type of intermolecular force here is that dipole. Oops. We'll talk more about these next time, but SiC is actually silicon carbide, which is a network covalent compound. So we'll talk about those more, not next class, but in a future class. You guys can learn more about them. And then finally, last but not least, we have CO. So that's carbon. It has a triple bond to oxygen, like that. Okay, guys, and our carbon is going to end up here because it has an electronegativity of about 2.5, while oxygen has an electronegativity of about 3.5. Carbon is going to be slightly positive. Oxygen is going to be slightly negative, leaving us with a polar compound here. So once again, this one is going to have dipole forces between it. Okay, guys, so